To chaos. We're in the middle of talking about one-dimensional maps, and so we started to discuss some of the simplest properties of the logistic map the last time, and we looked at how to calculate fixed points and period 2 points for that map, and also when they bifurcate, when they lose stability. So I'd like to begin here now by talking a bit about some of the more complicated aspects of the logistic map and its transition into chaos through a sequence of period doublings, which we looked at also a little bit last time, but we can go into more detail now. And so I thought the best way to do it might be for us to use some of the applets that are available on the web. If you just poke around on the web and search for a phrase like logistic map applet or period doubling applet, you'll find a lot of them. And I think that might be the easiest way to explore what's going on. You might also want to just write your own. But I posted several on our course webpage under resources, so you can fool around with the ones I'm showing here. So for instance, here's one that, let me turn out the lights. It may not be so easy for you to take notes, but I don't think you'll need to because you can reproduce this at home. Or of course, you can watch the video. You can watch this lecture again if you miss anything. Remember, we've got copies of all these lectures on video note. So how dark should we make it? How about like that? So can you see from the back there these little cobwebby structures? Are they visible? Yeah? And so what you can do with this, maybe I'll close this door. Do you think it makes a difference if I close the door? Should I make it even darker? No need. All right. So then you have two controllers here. One is you can control the initial condition of the map by moving this around. And you see the cobweb changes a little bit, but for the example shown, the iteration pattern just leads itself into 0. 0 is a stable fixed point for this setting of the parameter. Now the parameter can be controlled on this axis, which you see is increasing the maximum of the map. And we said that the max was at r over 4, where r was the parameter in the logistic map. So by changing the parameter, you're also changing the shape of the parabola. And you can see some interesting stuff happens. Like when we're down here, the iteration leads to the origin, whereas when we go up, now it's going to the right over to some stable fixed point. And that continues as we keep increasing r. At this stage, we're seeing what looks like a spiraling approach to the fixed point, right? We overshoot and spiral in, and then with a little bit higher value of the parameter, we're starting to see, bam, there's a little period 2 cycle you see in red, and that will get bigger. We're also seeing the transient behavior in gray, but the red is the attractor. And then that attractor just continues to get more and more exaggerated until at some point it should go to period 4. Now period 4 looks like this. That is, the red, single red curve splits into 2 red curves. So you can verify that really is period 4. We're going from very low up to, well, fairly high, then over there, then down, somewhat lower, and then somewhat higher, and back around. So there's actually 4 points in the cycle. And then if I have a really good touch, maybe I can make it look like period 8. Let's see. That's going to take some fine motor skills, which I may not possess. Still period 4. Oh, what's that? That might be period 8. Yeah. Now, I don't know. Period 16 could be tough. I don't know. Whoa. So, you know, because remember, the period doubling bifurcations happen faster and faster. And at some point, we'll be into the regime where it's chaotic. Now, what would that look like? Something like that, maybe. I mean, it's hard to tell if it's very high period or chaotic. Certainly, if there, we've gotten down to some low periodic orbit again. And then something complicated. We know if we go all the way to the top, that's going to be chaos at r equals 4. But anyway, you see this interesting mixture of windows of periodicity popping in there. Like, whoa, there's the big period 3 window. That is, notice there's 3 points in the cycle. Here, here, and up there. So that's period 3. And that should exist over a fairly big window. Well, not actually so big, maybe like 0.02. Yeah, it's not. It does still take some skill to move the slider and stay within there. But anyway, there's period 3. And now, this is one way of looking at it, just looking at the cobweb. But before I leave it, do you want to ask anything about what you've seen so far? Okay, so then the other way that we look at these sorts of phenomena, we said, was in what we called the orbit diagram, which I only sketched with chalk on the board, and it was a disaster, really. I mean, you couldn't see much. So let me jump out of this cobweb program into what the writers of the applet mistakenly, in my opinion, called the bifurcation diagram. Why do I say mistaken? Because normally in dynamical systems, bifurcation diagram should mean an object that shows both attractors and unstable invariant sets as a function of a parameter. So you want to show both like unstable fixed points as well as stable fixed points, and unstable periodic orbits as well as stable ones. And this kind of diagram is not showing any unstable objects. It's only showing stable things. So this is more properly called an orbit diagram, because it's showing the long-term behavior of the orbits, the trajectories. So, okay, that niggling point aside, and by the way, most people do call it the bifurcation diagram. I mean, I'm in the minority here, but whatever. So here's the bifurcation diagram, orbit diagram of the logistic map. Well, what's really nice about this, okay, remember what you're seeing. This parameter is called A here, but we called it R. And then what we're showing is if you let the system run for a long time at a given value of R, it will settle down to some attractor. And then you plot all the points on that attractor. So something like this represents period 1, because at this value of R, you just eventually end up at that point. Or at this value of R, you alternate between these 2 points. So that's what period 2 would look like. And then this sequence of splittings tells us we're undergoing period doubling from 1 to 2. Here's 4. 8 is there. And then it starts to get to be hard to see. The splittings, the pixels can't resolve it. And now somewhere where it starts getting very dark, we're in the chaotic region, but interrupted by these open windows of periodicity. Now, you can't see very clearly the periodic windows, but conveniently the writers of this applet have let us blow things up by just doing the obvious move, where you draw a little box, and then, bazinga, you know, you've got that. And it also conveniently shows you where you are in parameters. We're now between 3.5039 and 3.69. And you can start to see that there is quite a bit of structure, including what appear to be, I mean, now the periodic windows are popping out much more distinctly. But I had made this point, let me go back. I made this point originally that inside of each periodic window, you will see a copy of the whole bifurcation or orbit diagram. So to verify that, or at least experimentally verify it, let me go into the big period 3 window here and blow that up. And there appear to be suspicious objects like this one. If I blow that up, that's just an upside down copy of the whole diagram. And you see it has its own period 3 window, which can be blown up. And now you might wonder, like this little scrawny guy down here, what's his problem? Well, he's just scrawny, but he is a copy of the diagram. If you just change the scale, he's fine. So it's amazing. Now, look at where we are. Now we're between 3.8536 and 3.8541. And as you can sort of see, this fractal structure never stops. It's just going to keep containing copies of itself all the way down to arbitrarily small scales. And so one thing I want to try to discuss with you is why does that happen? That is, is that what your question was? Is that provable? Well, I don't know if, yes, it is provable, not by us. we will give an argument that contains the intuition for why it's true. And I think you'll be convinced. I don't know if I would call it a mathematical proof, but it's certainly what's going on, what I'm about to tell you in a few minutes. What else to say? Now, I also claimed the other day that there were periodic windows of any period you want, and not necessarily easy to find them, although there are algorithms for finding them if you specify the period. But let me show you that by going deep into the chaotic part of the picture. And I have no particular plan for what to look for here. But let me just kind of go into the maelstrom, where it's really messy, and just see what's living in there. So you see various white regions. I mean, some of them are pretty conspicuous, like this one. But why don't we go to a really thin one? How about over here? I have no idea what this is going to be. Like, it's hard to reach also. There's something white in the middle of my red box there. Oh boy, whoops, where'd it go? I don't know what happened. That should have worked. Well, try again. Let's try that again. Well, there's somebody. Now, I hope this doesn't go away when I zoom in on it. Don't be shy. What is going on in there? So now that, okay, what is that? I see 1, 2, 3, 4. So it looks like that's some kind of period 4 window. I could try blowing it up a little more. It's hard to reach the bottom and the top here. Not doing very well. I think it's period 4. It's all very difficult to observe, but like what's going on this one? No surprise, that's going to be the usual picture, I hope. Yeah. So that was, I don't know, maybe not so convincingly period 4. We could try looking for some other stuff. How about in here? There's a lot of windows in there. By the way, you might notice that there are some prominent curves running through the picture. Right? I mean, like you can sort of see what appears to be a curve going through here. And maybe you can see, looks like other curves are meeting at this corner. That's one of your homework exercises, to explain what those smooth curves are running through the picture. They're called supertracks. And there's a reason why they're there and why the iterates of the map tend to become denser there. So that can be understood analytically. That'll be something I'll guide you to in the homework. But anyway, just jumping in, like what is this? This appears to be period 1, 2, 3, 4, 5 in here. Let's just verify that. Yeah, there are 5 of them. Also, when people talk about fractals, they always say that this contains arbitrarily small copies of itself. But notice that they're scaled in different ways. Like this one looks wider than this one that I was referring to as scrawny. And you can see that there are different thicknesses in the x direction, that is this vertical direction. So don't get the idea that these are all perfectly geometrically scaled with the same scale factor. They're not. And so I'm going to make the point later in this lecture that the scaling factor in the x direction, that is this vertical direction, depends on where you are. And so, I mean, that's a subtle point that's often not noticed in the literature, but if you actually do simulations, you'll see it plainly. Yes? Oh, that's an interesting question. The question was, within a periodic window, like where I see a period doubling sequence happening in here, but there's presumably also one down here, are they undergoing their period doublings at the same time? Yes, they are. And that's because they're not really distinct from each other. That is, you might think this object is somehow separate from this one, but keep in mind they're all tied together in that, like when I speak of period 5, we're going to go from here to like maybe here to there to there. So they're all one object, the period 5 object. And so when period 5 period doubles to become period 10 in here, it's period 10 throughout the whole vertical. You know what I mean? That is, it has to be that they'll bifurcate at the same place because it's one object that's bifurcating. Yes? The question was, if bifurcations happen at the same time, how do we end up with anything other than powers of 2? Well, remember that the powers of 2 happen within a window, but the windows themselves can have any period. Like we've seen period 3 or period 5. So really I take your question to be, how do you create something like period 5 or period 3? Because they don't occur by period doubling. They're born in some other mechanism. And so let's look at that right now, actually. Why don't we try to understand period 3 and how it's born? Unless you have anything else you want me to do with this orbit diagram before we leave it. Yes?
Just a quick question. So it's possible for this map to have like 2 stable points, like maybe this 5 things that you're seeing could actually be composed of a 2 cycle and a 3 cycle.
The question was, could the map ever have 2 coexisting stable things, like a stable 2 cycle and a stable 3 cycle, and maybe what we're seeing when we call it period 5 is really just a 2 cycle and a 3 cycle both stable. No, that doesn't occur in this system. That is, we could show that there's only one attractor at any given parameter value. So I'm not giving you the proof of that, but that's known to be the case. Yes?
Any given cross-section, like vertical cross-section, if you're going from the minimum value to the maximum value, are you passing through all the points?
The question was, as you go in a vertical cross-section of this picture, as you go from the minimum to the maximum value, do you go through all the points, meaning what all the points, from 0 to 1, or all the points between the minimum and the maximum?
Yeah, between the minimum and the maximum. Like when you have like a period 4 cycle, you have like the minimum value and the maximum value.
When we have something like a period 4 cycle, we have the 4 numbers that we have. But you're saying, do they go, like, does the lowest of the 4 go down to the minimum of the map? Is that the question? Not necessarily. Because
no, if you're going from, like, you're looking at where the minimum value is and the maximum value, the highest value, like, versus across this time.
well, we can go back to looking at what the map does. That was, we can see it in a picture like, whoops, let's not do that one yet. I think it was this one. So what do you want me to answer here? I mean, like, here's period 3. So we went from this value on the curve to here's a value near the maximum, and then down to this value, which is low but not at the minimum down here. I don't know, is this answering the thing you're wondering about? Or no? I don't know. Let's leave it. Maybe you should play with these and then you can answer your own question. Okay, but so was there anything else about back to the orbit diagram? Yeah, anyway, yes, last one on the orbit diagram. Go ahead.
Is there any more detail inside the chaotic region? Like, does the interval contain an infinite number of windows?
Okay, so the question was, could we look at more detail inside the chaotic region? Does any region contain, does every region contain an infinite number of windows? Was that the question?
Yeah, I'm just wondering, like, what's going on there.
Yes, what is going on in the chaotic part? So when we speak about the chaotic region, you probably shouldn't think of it as, that there is no such thing. There's a mixture, an intermingling of chaos and periodic windows. And so if you zoom in on any region, and I don't know that this program has sufficient resolution, there are periodic windows all over the place. So although I can't see them here, but I don't know, I sort of think if I keep looking I would find them. No, I'm not buying it. It doesn't seem that this program's going to resolve it. They get very thin. But a different question might be, like, there's a very interesting question you could ask, which is if I pick a random parameter value, what's the chance I'll be in at a chaotic parameter value as opposed to one leading to periodicity? And people have studied that. And I'm not remembering what the answer is. I think it's something like you have in the chaotic part of the picture, or the part that looks chaotic, I think you have something like a 90% chance of being in a chaotic part as opposed to a periodic window. But you can read about that there's a homework, or no, I'm not going to assign it for homework, but if you search in the index of the book for the word fat fractal, there's a discussion of this question that I just raised about what's the measure of the chaotic versus the periodic part. So, all right, I'm not making the point very clearly in these diagrams that there really are windows all over, but explore for yourself and see what you find. But I did want to get back to this question of where did period 3 come from? Yes, I see another hand going up. Okay, go ahead, last one.
So you talked about the homework question, the dark curves.
The dark curves, yes. Oh, I already signed that question?
Yeah, we did that today.
Oh, you did that question for today, the supertracks. Okay.
But if you allowed a longer integration time when sort of you're generating this picture, would you eventually wash those out and sample all of the points in that region?
The question was, if you allowed a long enough, if you did many, many iterations, would you wash out the supertracks and just see a uniform distribution of, I assume this is your question, a uniform distribution of dots over the allowed region? No, the supertracks are real, and if you integrated, or that is to say iterated longer, you would just, the way you should think of it is that across the attractor, across any vertical strip, there's a probability distribution. Think of it as a kind of histogram. And it's a so-called invariant measure that is sitting there. And so the longer you sample, the more you will sample the peaks, and the less you will sample the relative minima. And so the supertracks are actually singularities of those invariant measures. They're places where the probability, well, I mean, they're regions of very high probability, let's put it that way. So that's why they're so dark. Okay, but anyway, jumping out to the question of where do those other periods than period 2 come from, I think this one may show us that. That is, all right, here you see the standard map, standard picture of the logistic map. And what this little applet allows us to do is do things like graph instead of just the function. I can remember in our last lecture we talked about the usefulness of looking not at the function but say f of x. Like when we wanted to look for period 2, we said those are fixed points of the second iterate f2. So this thing lets you type in the composition that you're interested in. Uh-oh, what happened? Can I not type? Maybe I have to reload this program? I don't know. Let's try that again. Okay. So here it's asking for a number. My screen isn't showing all the words, but at the moment it's showing the third iterate. But I could look at the second iterate. And let me, I don't know, say forward. And what it's showing is the second iterate, but maybe you can perceive that it's moving a little bit. And that's because it's sweeping the parameter. That is, here's the current value of the r parameter. And so as you change the r, the trough is getting lower, the peaks are getting higher. So we're looking at f2 of x as we change the parameter r. And now why is that a good thing to do? Well, this will give us a clue for how period 3 is born. Let me look at, if I change this to 3, let me pause the program here, pause, and then make this number 3. And I want to show you what the F3 looks like. Let's say I go to some value like, I don't know, 3.6. All right, so there's F3 of x, some shape like this. Let's just inspect it for a second. So that's f of x versus x. And you'll notice it has 4 maxima, all the same height. Right? There's 4 local maxima. And what's going on? So like here's where the origin is. Remember, that will satisfy f3 of x is x because the origin is a fixed point. So after 3 iterates, it'll still be at the origin. So you go through there. There's also this fixed point, which is just that thing that we called x star the other day. That's the fixed point for f itself. So it too will repeat after 3 iterates. But then we're not seeing any other intersections of f3, its graph, f3 of x's graph, with the diagonal. What does that tell us? If f3 of x does not intersect the line y equals x, what does that tell us? Yes? That there are currently no period 3 points for f. Right? Because a period 3 point for f would mean a fixed point for f3. And so the fact that f3 does not intersect the diagonal except at the trivial points tells us that we're not yet in the period 3 window. We don't have any period 3 orbits yet. You buy that? You want me to repeat the argument? Want me to give you amphetamine? Wake up a little? Okay, well, I don't know what you want. But what I'm going to do is start increasing the parameter value, r, and keep your eye on the birth of a period 3 point. What is it that creates the birth? So let's now go forward. Can you see what's about to happen? Boom. The curve crossed through. Let me go back to that moment of excitement. Just a moment after this, we're going to have 3 things happening simultaneously. That is, you saw that this trough was coming down, and so was this trough coming down, and then that max was rising. Right? And they're all going to simultaneously hit. Let me go backwards again so you can watch that happening. Okay, let me now go forward. Okay, watch. Boom. There's a simultaneous tangency at 3 places. Did you see that? That's what we want to understand. What is going on there? That's a new kind of bifurcation for us. That's not a period doubling bifurcation. Those are called tangent bifurcations, where the curve became tangent to the diagonal, and it happened at 3 places simultaneously. Should that surprise us? That it happened not just at 1 place, but at 3. It's not surprising, because it has to occur at 3 places simultaneously, because we're creating a period 3 orbit, which has 3 points in it. So if it happens at 1 place, it's going to happen at 2 more. And this period 3 orbit is born in this tangent bifurcation. And now for a really interesting point. Watch what's going on as we keep going a little bit farther forward. Let me just go a slight bit farther forward and then stop. Look at what happened after period 3 was born. This might not be obvious to you, what I want to say here, but so period 3 was born, let's say, at that place as well as the other 2. But just look at the shape of this graph right here. Forget about anything else in the picture. Whoa, do you see what I'm driving at? You're snickering. Why were you chuckling back there? Yeah.
It looks like the exact same structure, just starting to repeat.
Yeah, it looks like the logistic map, right? The answer was it looks like the same structure as before. Yeah, this thing looks like a little upside down parabola, which is what the logistic map looks like, except it's small. Yeah, that's right. And so when we said that once a window is created, it's going to undergo period doubling and have its own window and have its own bifurcation structure. That's why. Because when the tangent bifurcation occurred, this looked like a parabola touching a line, which then pops up to become a taller parabola. And it's just the same old scenario in miniature. And that's the main point. That's why the diagram keeps repeating itself. So let me write that on the board just so you can make sure you got that. But that's the essence of it. And so when you asked earlier, is there a proof that these windows all keep going and have miniature copies, that's the proof, or the essence of the proof. Yes?
Also, when we know that one, the parabola opens above the curve, but for the other 2, after the point of tangency, because they're going below it, does that give us any intuition as to why, when we look at the period 3 on the orbit diagram, we have a negative looking?
Right. So the comment was, we see that at these other places where the intersections occurred, like here and here, these are parabolas opening downward, whereas the other one was a parabola opening upward. Does that give us any intuition about why, when we looked at the bifurcation structure? Actually, people often call it a fig tree, this thing where it splits and splits and splits, in honor of Feigenbaum, who did a lot of the studies of it, Feigenbaum being a German way of saying fig tree. And so this fig tree, I believe, according to that, we should see that the fig tree would kind of open downward for this one and this one, but not for the other one. And also notice that this little parabola is thinner this one is wide. So we would predict maybe based on that the reason that there's different scaling in the different parts of the picture is because of these different thicknesses. So here, this one should be wide. This is the one, maybe actually this last one is the one I called scrawny, or was it this one? Let me just see. Should we try to look? Let me jump back to the orbit diagram and see. If I zoom in on period 3, so we're predicting the two bottom ones will be going down. And that appears to be right. And this lowest, the scrawniest one is this one on the top. I mean, that has a scale going from 9.2 to 9.7. If you, well, probably I ought to look at it from up here. I mean, it's sort of thickness. I've messed that up. But anyway, it's on the order of 0.01 in thickness, whereas the other ones, like in here, I don't like the way I just did that, but oh, you can see I'm obsessed with playing with this. Anyway, they are going down. They're going down as you guessed. So yes, these much simpler pictures of looking at F3 can give us a lot of insight. Yes, one more question before we hit the board. Yeah.
But in a picture like this, how does that? So with period 3, you only have one period 3 window in the entire orbit diagram. In some you said the last time. But for periods that occur more than once, so some odd number of periods that just shows up more than once, how does a picture like this show the second birth of that?
Okay, this is an interesting question. That the period 3 window appears only once in the whole diagram, and so a picture like this can give insight, whereas something like period 4, which occurs in various places, how could such a picture give us insight? Well, I don't off the top of my head know the answer. We could look at a few different, say, period 4 or period 6 windows and see how this picture changes. It'll be a little bit different in each of them. Though I don't know that I mean, maybe you should do it yourself. Okay, I mean, I don't know offhand. We could wander into that question. I mean, it's an interesting question. I don't really know what to tell you. Do you really want me to do it now? No? Okay, I don't mind doing it, but all right, maybe I won't. But yes, I mean, I think you have the tools here to explore it. You can find some other periods, and I'm sure you can find various period 6s and 4s and compare their diagrams. It's fascinating. There's a lot to do with this kind of thing. Yes, please. Do we have multiple period 4s? We do. We know that we saw one period 4, the kind of silly one that went period 2 to period 4. But there's another period 4. I thought, didn't we see one earlier? Or maybe we didn't. Let's hunt around for one just for a second, since you're indulging my obsession here. Refresh. I don't know. I think there's one in here somewhere. I see a period 6. There's 1, 2, 3, 4, 5, 6. Period 4, where are you? Well, this is a 5, isn't it? Yeah, there's a 1, 2, 3, 4, 5. Well, I don't know where it would be. Did we talk about one earlier? I don't remember. I don't remember where they are. Oh, was it maybe in the back somewhere? Well, there's a lot of stuff back here. Period 5, period 3. What are these guys? What's this one? 1, 2, 3, 4. Is this one a 4? There might be a 4 over here. Okay, let's check that one out. That's a 4. Yeah. So, and I suppose if we want, we could get the parameter. Let's do this for the heck of it. I mean, I don't know what's going to happen, or whether it'll even be interesting, but I mean, I want to explore this question. I'm trying to zero in on the parameter values. So it looks like if I say 3.96, I will be safely in the period 4. So let's jump out of there and type in, what did I say, 3.96? I don't know, is this going to be interesting or not? 3.96, I don't want it to have any change in A. I'll just fix that. And I don't need that at all. I'll just say 3.96. And what should we do? Ask for the fourth iterate. And then say forward. Does it work? So there's a picture of f to the 4, f composed with itself 4 times. And what am I seeing? Looks like 4 almost tangent intersections, right? 1, 2, 3, and 4. And these two, well, the trouble is it's hard to resolve what's going on. But it looks like these are going down. Right? Those are upside down. And then this is another upside down one. And that's an upside up one. So I don't know. What question were we asking? I forget. How did we get multiple parameter sets to give us the same periodicity? So
anytime we have an intersection that's not close to tangential, it's not stable.
the statement was anytime we get an intersection that is not.
The intersection of the x equals y.
Yes?
So we've got a bunch of intersections there, but the only ones that will lead to periodicity.
Oh, okay. The comment was we see a lot of intersections that are very steep. Yeah, those steep intersections correspond to unstable periodic orbits of period 4. Yeah, the ones that are going to be stable are the ones where the intersection has a slope less than 1 in absolute value. So on this picture, they're going to look close to tangential. Okay, man, so many questions. I don't know what to do. I've never taught a class like this, especially on tape. All right, I'll take 2 more, and then I'm going to stop. Go ahead. You could go first.
So, even though like you find like multiples of things, one, is there some sort of structure as to how like all the prime number periods are positioned?
Okay, questions are like, how are the prime number periods positioned? How are the different periodic windows arranged? There is a story about this. There's something called the universal sequence. So, or the U sequence. And if you look in the book, I discussed the universal sequence. What's universal about it is that it tells you the order in which the periodic windows will occur in any map that looks like the logistic map, meaning it has a roughly upside down parabola shape to it. And it's the same sequence for all of them. And it can be seen in experiments, and it has been seen in experiments on chaotic chemical reactions. So it's a real thing. And it's not easy to say what it is. I mean, you'd have to study it, but it's known, and it obeys certain combinatorial rules. And I should have probably said earlier in response to a question like, how do we distinguish the different period 4s? There's a pattern that people look at where they look at the sequence of the points in the orbit. Are they to the left or the right of the maximum of the map? In this case, a half. So you can ask, as you hop around on the map, are you going? You can write a word for the orbit, like RRLL, or RL, whatever. Sequence of R's and L's for are you to the left or the right of the map. They call it the symbol sequence of the map, of the orbit. And the symbol sequence distinguishes the different period 4s or the different period 6s or whatever. And so the analysis that leads to the universal sequence is an analysis of what RL sequences are possible. You can show certain of them are impossible, just from the shape of the map. And so that leads you to all kinds of insights. But I wasn't planning to get into any of that for now. So please explore all this if you're interested. But let me jump out to the blackboard now. I think I'm ready to do that. Okay. Wakey, wakey. All right. So all these, as I say, are on our Piazza course page. They're the top. And I also gave a few more applets if you want to poke around with them. Okay, let me blank out the screen. All right, so I hope it's now become clear how the periodic windows are born through these tangent bifurcations, why they each have their own period doubling sequence inside them, because they each look like little logistic maps near their tangent bifurcations. And I guess that's about it as far as what I wanted to say about the logistic map. But now let's turn the discussion to the universal aspects beyond the logistic map. And I would say this is the hardest thing we're going to discuss in the whole course. So you may want to amp up your brain power a little bit. That is, the rest of this lecture and the next 1 or 2 lectures will be at a higher level of abstraction and difficulty. But I think it's worth doing it because this is, to me at least, maybe the highest high point in the whole subject as far as intellectual payoff. So let's try to understand it. It's discussed in section 10.6 and 10.7 in the book. And the work that we're going to discuss is from Mitchell Feigenbaum. Published in 1978, Journal of Statistical Physics, volume 19, page 25. That's a pretty hard article to read, I would say, but there is an easier one by him that is better exposition, really, more readable. In 1983, in Physica D, Physica D, volume 7, and it's page 16. So Feigenbaum is an interesting character. I'm going to write, I'll post another chapter from James Glick's book, Chaos, where he talks about Feigenbaum. Just a little background, it's interesting. He was working at Los Alamos at the time, and you'll have to look at a picture of him. He's kind of fantastic looking, or certainly he was as a young man when I used to see him at conferences. Have you ever seen pictures of Beethoven with the kind of crazy hair and intense eyes? And this is what Mitch Feigenbaum looked like. Find him on the web, especially his younger pictures. So very, very brilliant guy. And he was known at Los Alamos as sort of like, in a place where there's a lot of smart people, he'd be the smartest person in the room. But at that point in his career, he hadn't solved any really big problems. Certainly nothing commensurate with his ability. And so it must have been frustrating for him to be the smartest, but not the most accomplished. And so he was trying to find something big to work on. And he, at least that's the way James Glick tells it. And so he also had this odd sleep pattern, which some of you graduate students might have, in which he was out of phase with the rest of society. That is, he would just stay up as late as he felt like, and found it was really good to work on the computer at night when things were quiet. And so he would go to sleep maybe 2 in the afternoon or something, and then wake up to go. So, and also he used to walk around on the streets of Los Alamos in the middle of the night thinking about difficult problems. And so the police got familiar with him. Not that he was causing trouble, but they would just see this guy wandering around in the middle of the night thinking. And so he was very interested in turbulence, but also just the more general question of where does chaos come from in nature? What causes disorder? And why are some things orderly? And he was looking at clouds. He was thinking about eddies in whirlpools in water. And anyway, this somehow led him to think about the logistic map as a simpler model of the transition by which systems go from orderly into progressively less orderly and finally into chaos and disorder. And so he did this deep study. As I said earlier, that the logistic map had been studied since the early 60s. But Feigenbaum really made a very penetrating analysis of it. And has since certainly lived up to his potential. I mean, he's won all kinds of awards for the discoveries he made about this. But curiously, when he first tried to publish his work, no one could understand it, and it kept getting rejected. And so I think these discoveries that we're going to talk about were made several years earlier, like around 1975. And his paper got rejected at least 2 or 3 times. And so this one finally did get published. But really nobody knew what the heck he was talking about. Anyway, but now we do. So, well, anyway, so what did he do? He certainly studied period doubling. In various maps whose graphs look like the logistic map. Let me call them one-humped maps. The word that's often used is unimodal. Sounds a little nicer than one-humped. But anyway, a unimodal map would be something that just has a single smooth maximum. Something like this, xn plus 1 is a parameter r times a function of xn with the shape of the graph sort of looking like this. There's f of x as a function of x. Just has a nice single max. Like the logistic map, it doesn't have to be a parabola, though. It could be anything with that shape. And what he found was amazing quantitative laws that were independent of the precise form of the function f. So I'll put an exclamation point on that because it seems like magic that you're putting in something that is not very strong, just a map that's smooth and has a single maximum, and yet you're getting out numbers, precise information that doesn't seem to depend on the details of f. So that was very mysterious, and then yet he was able to explain that by making connections to statistical physics. So specifically, he found an analogy to what the statistical physicists call universal exponents. And so these universal exponents are observed in phase transitions, second-order phase transitions. In all kinds of different physical systems, like magnets, fluids, superfluids, and so on. It's just a big story in statistical physics. That is, maybe I should just tell it for a moment, partly because it's a Cornell story. That is, we have Professor Whittam, Ben Whittam, here in the chemistry department still teaching. Former professors Michael Fisher, Ken Wilson, who won a Nobel Prize for this kind of thing. They were all interested in phase transitions. And the observation was made by experimentalists that at phase transitions you could often measure power laws for things like how does the magnetization, that is the tendency of the magnetic spins to line up, you know, a measure of how lined up they are. How does magnetization depend on temperature? So you'd have a graph that looks like this. So the amount of magnetization as a function of temperature. There's some critical temperature, you know, where a magnet, if you heat it up too much, there's so much thermal buffeting of the spins that the spins get disordered, and now it's not really a magnet anymore. Doesn't act like a magnet, it's a paramagnet at that point. So as you raise the temperature, the magnetization becomes 0 at some critical temperature, which we'll say is here. And then, below that, the thing starts to act like a magnet. So it has a positive M. And so there's a T critical, at that location. And what people are interested in is how does the magnetization depend on how far away you are from the critical temperature. And the finding was that the magnetization would grow like the distance, that is T minus T critical, absolute value, to some exponent that they would call beta. That is, would grow like a power law. So I've drawn the picture here like it sort of looks like a square root function. But it may not be a square root. It could be some other exponent than a half. And so they would measure these exponents beta. And the part that was amazing is that here you were studying a magnet. Then you could study some other system that undergoes a phase transition, like a superfluid or an ordinary fluid or something else. And under certain conditions, they were measuring the same exponents for systems whose physics was totally different. And so that was a big shock. Like, how could this thing, which is classical, and this other thing, which is quantum mechanical, or whatever, and they have totally different mechanisms and different laws of motion, they're showing the same beta. So if you take a course in critical phenomena, you'll hear about this. It was a giant story, and it was eventually explained by the people who developed the renormalization group, of which Ken Wilson was the one who got the Nobel Prize. But a lot of people contributed to it. And so anyway, that's the sort of the, well, Feigenbaum found a way to use these renormalization ideas to explain what what we're going to talk about that he discovered. So Feigenbaum used, and I'll try to explain what we mean by renormalization to explain this universality that he saw. Just as Ken Wilson had used renormalization to explain the universality that the physicists had seen in critical phenomena. So there's that. I mean, the connection to statistical physics was amazing. This really got people's attention. You had this very well-respected branch of physics that was winning Nobel Prizes, turning out to be useful in this totally flaky fringe area of chaos, which up till then hardly anyone took seriously. It wasn't even a field. It was just a bunch of goofballs, from different areas working on this thing. But none of them are getting hired. None of them are, like I say, there's Feigenbaum out in the middle of the night. People say he's kind of a disappointment. He's got so much potential. And there's Ed Lorenz with his monotone, studying the weather. And everyone says, your model's all wrong. This is not how weather really works. He says, I know, but don't you understand what I'm saying? You have to understand that chaos was this real, scrappy outsider subject that nobody took seriously. And maybe to some extent they still don't. Actually, I had a very unpleasant conversation with Neil deGrasse Tyson, who some of you may know from television, who's currently doing the show Cosmos. And the one time I was at the World Science Festival, seated next to him eating dinner, my wife, his wife, and he says, oh, you work in chaos theory. That never amounted to anything, did it? And there's really nothing to your subject as far as I can tell. Of course, it makes for a lively conversation when someone says something like that. But so there may be a lot of folks who don't yet know, and I couldn't give them the whole course over dinner, but I certainly don't agree with him. Anyway, so yes, we have been seen as outsiders for a long time, but after Feigenbaum, I think anyone who was paying attention, realized that there was a lot to this subject. So the other thing, though, is that in addition to renormalization, Feigenbaum's work, so this was A, the analogy, this is B, the use of renormalization. And then the third point that I wanted to make here was that Feigenbaum's work led to predictions really testable predictions about the route to chaos in all kinds of different systems. Not to say every system that goes chaotic will follow the period doubling scenario, but if it does follow period doubling, then Feigenbaum makes strict predictions about what's going to happen, and those predictions were confirmed again and again in very, very different physical systems, and not even just physical, chemical and biological. So confirmed in later experiments on fluids, chemical oscillations, semiconductors, etc. There were tests also done in things like heart cells where the data weren't quite as clear. And then people started getting carried away and tried to apply it to the stock market. And there got to be a little bit of a backlash because but some people got a bit carried away with the predictive possibilities of chaos theory. And all right, so that part is not a shining moment in the history of chaos, but certainly for these well-controlled systems in physics and chemistry, it really did work. Okay, so let me now try to say what's universal? What are we talking about here? So imagine doing a computer experiment like this. And Feigenbaum himself did such a computer experiment. Instead of considering the logistic map, take another map that is called the Sine Map. So f of x is r sine pi x, where x goes between 0 and 1 as before. For the logistic map, this has this kind of qualitatively similar shape. It's just an arc of a sine wave. Its maximum is r at x equals a half. And remember, for the logistic map, the maximum was r over 4. So if we're going to compare these, we want to scale by 4 to make up for that difference. But anyway, you can study this. And of course, it's very different from the logistic map because the sine function has a Maclaurin series that includes all odd powers of x. All right, I mean, it's x cubed over 3 factorial, etc. So this is a transcendental function. This is not a simple nonlinearity the way x squared was in the logistic. Yet, if you draw the orbit diagram for this, you get a picture that looks essentially the same as Feigenbaum's, or as the one seen in the logistic map. That is, as a function of r, we see the same story of, 0 is stable up to a certain point, then a branch, then the period doubles, then those period double. There's a period doubling sequence to chaos. And then in here, we see the same story with chaos and periodic windows mixed together. The parameter values r, where these things happen, are different than what we had before. They have to be. It's a different function. And so this was known before Feigenbaum, that you would have this period doubling, again, even for that map. And the periodic windows had been studied and so on. So people knew some of that. But what Feigenbaum was really interested in was the details of this period doubling cascade leading to chaos. So he certainly observed that the things that we called the RNs, that is where the period 2 to the n orbit was first born, he observed that the specific RNs depend on which map he was studying, Sine Map or something else. So those depend on f of x. But what about if we look at that ratio of the gaps? That is, if we look at the thing I wrote down in the last lecture, Rn minus 1 over Rn plus 1 minus Rn. If we look at that as we approach the onset of chaos, that is here on this, at this limiting point, R infinity as we call that. If we look at this, this approaches again some number. And it turns out to be the same number. 4.6692, that number that I call delta. Just as in the logistic. And so let me read you a quote from Feigenbaum about that because I like it. In the book, you can see a picture of the two different orbit diagrams for the two cases. I didn't pass it out today, but you know, I mean, you have that diagram in the book. You can see how similar they are, but also that there are differences in the details. Still, so Feigenbaum, it turns out, was really interested in these RNs, and he had a theory for them for the logistic map. I mean, he was trying to calculate them analytically. We saw we could do a few of them, but he wanted to explain them all. Well, so he had a theory based on generating functions to calculate them. And so he had tested his theory. You know, of course, they have good computers at Los Alamos, some of the best supercomputers in the world. But he wasn't especially good at that kind of computing. He was good at using handheld calculators, which were very high technology at that time. You know, the idea that you could program your calculator, that was astonishing in 1975. And so he would program his calculator to look for where the next RN was going to occur. And he says that this is how he discovered this rule for the logistic map. But then he says he wanted to try to understand, what is this number? Like, is it pi squared over 6? Or, you know, what is that? So he says, I spent part of a day trying to fit the convergent rate value, 4.669, to the mathematical constants I knew, e and square root of 2 and stuff. The task was fruitless, save for the fact that it made the number memorable. So he didn't get it to work, but at least he drilled this number into his head. He says, at this point, I was reminded by Paul Stine. So Stine was a well-known mathematical physicist at Los Alamos, who you could picture probably having lunch with Feynman or maybe it would be breakfast for Feynman and, you know, whatever. But so they're talking, and Stine says, Stine had worked on the universal sequence that I mentioned earlier about periodic windows, so he knew a lot about these problems. He says, I was reminded by Paul Stine that period doubling is not a unique property of the logistic map, but also occurs, for example, in the Sine map. However, my generating function theory rested heavily on the fact that the nonlinearity was simply quadratic and not transcendental. In other words, Feynman had a theory for the logistic map. He didn't have any theory for something like this. So, and the fact that there's still period doubling in both, but his theory only works for quadratic nonlinearity, he just realized, well, I'm on the wrong track. So he says, so accordingly, my interest in the problem waned. But then he says, perhaps a month later, I decided to recompute the RNs in the transcendental case, that is, for the Sine map, numerically. The problem was even slower to compute than the quadratic one, meaning in his handheld calculator. It's taking a long time. And that was a good thing because it meant that he could try to guess what the next value would be in his head. And so he would wait, and then it would see that it would work. Now he noticed, he said, again, it became apparent that the RNs converged geometrically. And altogether amazingly, the convergent rate was the same 4.669 that I remembered by virtue of my efforts to fit it. So he saw this number coming up again. He thought, this is a strange coincidence. So then he did teach himself how to use the supercomputers, and he computed the number to quadruple precision. So, you know, like 64 digits or something. And they agreed to 64 digits. So he realized he was onto something, and he did it for several other maps, and he kept getting the same thing to 64 digits. So that was then the question, what is this number, and how to explain it? And so that's what I want to try to get into now. By the way, we don't know what the number is. It's not, as far as we know, anything related to pi or e, but it's just Feigenbaum's constant, delta. Do you want to ask anything before I continue? Okay, so this refers to a kind of universal scaling occurring in the parameter direction, in the r direction. And there's also universal scaling in the x direction. which he discovered too. So by that I mean, if you think about the those little period doubling fig trees that we discovered in each of the periodic windows, we saw some were wide, some were thin. I was calling some scrawny. So he wants to try to calculate something about that, the width of the scaling in that direction, or the width of the fig trees. So in other words, let's draw a little picture of this. Suppose I have something like this. Here's one part in the fig tree, and then here's a splitting into something else. He wants to calculate something about this distance compared to when this then bifurcates. How does that compare to this distance? That's what we're talking about. And we saw that that sort of depends on where you are in the picture. And so to normalize for that, he looked at everything that's occurring close to the maximum of the map. That is, if we have a map that's roughly logistic looking, it has a maximum. We said it has a single maximum. So we look at near X maximum, we try to pick the part of the picture closest to that. And then the definition, this is a little complicated, but it's necessary because the scaling in the X direction does depend on X. So the way he controlled for that is he's going to, well, let's look again on the fig tree picture. If I think about where the maximum occurs, so this would be a half in the case of the logistic, or the Sine Map for that matter. So here's 1/2, and we're looking as a function of r. And then our picture, is going to involve the fixed point is coming up, it crosses through a half, then we get some period doubling at some point. We have this, and then we might have like sort of a skinny one, and then a fairly fat one. After these bifurcations occur, they're supposed to be occurring at the same r value. So what he would measure is distances measured relative to xm. So that is, in this picture, we would define this distance. That is, I'm measuring from xm the distance to the nearest xm will go through there. So I don't look at that. That's distance 0. I look from here to there. And I'm going to call that distance dn. And then I compare that distance to what I get if I look again at the next intersection with the max. You might wonder, how do I know for sure that these branches will intersect with the max? That's a good question, but they do. You can verify that. It's because at the max, the slope is 0, and this will create what we're going to discuss later are called superstable points or cycles. And so there are superstable fixed points or cycles of every possible period. And so they all, eventually all these limbs of the fig tree intersect the max at some place. That's not clear, I realize, at the moment. But when we talk about superstability, you'll see what I mean. But anyway, so that's the definition of dn. The next one would be this. That's dn plus 1, the distance from xm to the next part of the branch. And so the thing he's interested in is this ratio. dn is bigger than dn plus 1. It also always has the opposite sign. That is, if this one is going up, this one will be going down. And he found that dn over dn plus 1 converged to a number that was always negative 2.5029. That is, it's the same number for the Sine map, the logistic map, or anything else with that qualitative shape. And it's always this number, which has now come to be called alpha. And so we want to understand that scaling factor as well as the delta, the scaling in the parameter direction. Want to ask any question at this stage? Yes? The question was, does the width of the second doubling relate to anything? This one? This can be expressed in terms of alpha, I think, but it's not just going to be alpha itself. So there's a whole complicated story about how the scalings of the other bifurcating branches depend on alpha, but let's not go into it. The simplest one is this one closest to xm. But they're not just scaling the same way, as you can see. Yes? The question was, could you have also chosen the point from the bifurcation? Yes. Yes, you could look at that and that distance, or this and this distance. Yes, you could do that too. That would actually scale with alpha, I'm pretty sure. But so he phrased his analysis not in terms of points like this, but the points where you cross through xm. You might wonder why do that. And the answer will be clear to you if you ever look at bifurcation or orbit diagrams in a book or generate them yourself. The answer is that these points at the splittings are very hard to calculate accurately. The computation slows down near these points. It's hard to resolve them. Whereas at these super stable points where these intersections are occurring, the computation is very fast. And so it's just better for numerical reasons to do what he did than what you're suggesting. So I guess I'm close to being out of time. So maybe I'll stop there. And we'll begin next time by talking about superstability and how that leads into his renormalization analysis.